First of all, it shows us that that initial explanation isn't really right. We can't really explain why salt is ineffective at cold temperatures because of eutectics. Because what we just saw is that as long as you're above the eutectic, I mean, I grant you, below the eutectic, there's nothing going to happen. But as long as we're above the eutectic, as long as we're above -6, salt has got plenty of ice melting capacity. We also saw that, again, it's not due to ice melting capacity, that it's not the case that salt has too little ice melting capacity at cold temperature. It's got tons of ice melting capacity at cold temperature. The reason that salt is ineffective at cold temperatures is not because it doesn't have ice melting capacity, it's because it has a slow ice melting rate. You can think of salt as being like a reservoir or a well of ice melting power. At warm temperatures, when you pull the plug, that well drains quite quickly. The ice melt comes gushing out at a fairly fast rate. At cold temperatures, that well is getting plugged up. And when you pull the plug, the ice melt just trickles out in a little stream. Now, why is this important? Because either way, it doesn't work, right? Why do I care about this? I mean, if it doesn't melt fast after 1 hour, it's not going to be practically useful to me. Well, here's why it's important. Remember what I said earlier. Ice melting capacity is carved in stone. If the reason that salt was not effective at cold temperatures was because it had no ice melting capacity, there's not a thing in the world we could do about it. Ice melting rate, on the other hand, is not carved in stone, and it can often be manipulated by changing the chemical system. So if there is a way that we can manipulate our system, we may be able to pull the plug on that well of ice melting at cold temperatures and get it to gush out more quickly and activate salt at cold temperatures. So that's why this is an interesting observation. Now, how do we do that? Well, we're currently exploring ways that we can improve the performance of salt at cold temperatures. But as an industry, we're already aware of one way to make salt work faster at cold temperatures, and that's by pre-wetting. We know by long experience that wet salt works faster than dry salt does. However, no one's done a really careful study of either why that occurs, what's causing it, or trying to actually measure how much of an increase in ice melting speed we're getting by pre-wetting. So this is what we wanted to do. We wanted to apply those improved ice melting test methods to this question, and that's what we did. We looked at trying to answer some of these questions. What is the relationship between pre-wetting rate and the ice melting speed? How much pre-wetting liquid is enough? What's the optimum amount of pre-wetting liquid? How does the chemical composition of the pre-wetting liquid affect the ice melting rate? Well, I don't have time this morning to go into the details of how we ran these experiments. But just in brief, let me say that essentially what we did was we did experiments like I described at the beginning, where we measured the ice melting on blends of salt with different liquids. And we did it in a way that enabled us to isolate the ice melting component of the liquid from the salt. So what that enabled us to do is to see what effect does the liquid have on the ice melting of the salt itself. Because it's not the case that the liquid does its melting and the salt does its melting independently, and you just add them together to get the total. The liquid actually makes the salt itself melt faster, and that's what we wanted to nail down. Now this is what we saw. So this graph shows you the ice melting rates measured on a 50-50 blend of rock salt and different pre-wetting liquids over a period of time. This pale blue line here is our baseline. This is my ice melting rate of just dry salt at a temperature of -4 Fahrenheit. This first purple line is what the ice melting, again, what we're looking at is of just the salt component, just the solid salt component, when it's been pre-wetted with plain salt brine. So that tells us basically the effect of water. If we make salt wet with water, we're not adding any other chemicals. It's the same thing as pre-wetting it with salt brine. There's no chemical change, it's just wet now. And what we see is that just making the salt wet does indeed give me a substantial increase in ice melting rate at cold temperatures. What's even more interesting is look at this dark blue line here. This dark blue line is salt that's wetted with a mag chloride liquid. And note we get a much larger increase. in my ice melting speed with mag chloride brine than I do with plain salt brine. So, what does this tell me? It tells me there's a chemical effect going on. It's telling me that it's more than just making the salt wet. It's not simply that the salt gets wet and that helps it to dissolve faster. I mean, that probably is the mechanism, that the liquid is helping the salt to dissolve faster. But it's more than just being wet with water. Because if that's all that it was, what we should see is that it shouldn't matter what we wet it with. We can wet it with anything, provided that it is liquid at our de-icing temperature, and we can just look for what's the lowest cost liquid that we can put on and have the maximum amount of water. Well, that's not what we see. What we see is there is actually a chemical effect, that some chemicals, some brines will accelerate the ice melting of salt more than others.